Have you ever just stopped and wondered how we get a simple piece of rock to do our taxes, or find us a date, or even land a rover on Mars? I mean, it really feels like magic, but it's not. Today, we're going to hack the code. Not the software, but the actual physical reality of how a computer thinks. We are going to build one from the ground up, starting with a really simple, kind of strange question. So how do we trick a rock into thinking? It sounds like a riddle, right? But it's honestly the fundamental question of all modern computing. That rock is silicon, and for the last 70 years or so, we've gotten incredibly good at manipulating it. By zapping it with electricity in very, very precise ways, we can actually force it to do our bidding, to think, to remember, to create. And it all starts with a simple plan. So, what's our blueprint for building this thinking machine? It's this: a college syllabus. No, really. Think of it less like homework and more like our treasure map. Every section is a new clue, a step that takes us from raw sand and electricity all the way to a fully functional digital brain. So let's start with the first, and honestly, the most important step: teaching our rock how to talk. Okay, first things first. Before we can build anything, we need a language, a way for our machine to represent and understand information. This is where we learn to speak its native tongue. You know, the language of computers is probably the simplest one you could possibly imagine. It's called binary. It only has two letters. The best way to think about it is like a light switch. Is electricity flowing? Yep, that's a 1. Is it not? That's a 0. On and off. Yes and no. That's literally it. Now, it seems incredibly limited, I know, but as we're about to see, from these two simple states, we can build infinite complexity. So if binary is the alphabet, then Boolean algebra is the grammar. It's a set of really simple but powerful rules for messing with those ones and zeros. Think of it like a logic puzzle. The AND rule says if you have two inputs and both of them are ones, then your output is a 1. Otherwise, it's a 0. The OR rule says if at least one of your inputs is a 1, then the output is a 1. These super simple rules are the bedrock of all digital logic. Okay, so how do we make this grammar a physical thing? We do it with logic gates. These are the verbs of our machine. They are microscopic electronic circuits, and each one is built to do just one single Boolean operation. An AND gate is a physical device that takes two electrical signals and only spits out a signal if both inputs are on. A NOT gate is a circuit that just flips the signal. These are the tiny little action heroes of our digital world. So, we've got our alphabet, our grammar, and our verbs. Now we can start putting them together to form sentences, or, in our case, circuits that can actually think. This is where we make the jump from simple logic to actual math. By wiring these logic gates together in all sorts of clever ways, we create what are called combinational logic circuits. Now, the key thing to understand about these is that they have no memory at all. They're kind of like a goldfish. Their output at any given moment depends entirely on the inputs they are getting right now. Just think of a simple calculator. You punch in 2 plus 2 and it shows 4. It has no idea what you did a second ago, and frankly, it doesn't care. So how do you actually go from an idea like, hey, I want to add two numbers, to a physical circuit? Well, engineers follow this 4-step process. First, you state the problem. Then, you create what's called a truth table, which is just a chart that maps out every possible input and the output you want for each one. It's like your cheat sheet. Then, you use that Boolean algebra we talked about to turn the table into a formula. And finally, you draw the circuit. It's a surprisingly elegant process that takes you from pure logic to real-world hardware. And what can you build with this method? Well, all the fundamental building blocks of any computer. You can create circuits that add and subtract. That's the heart of any calculator. You can build magnitude comparators that can tell if one number is bigger than another, which is absolutely crucial for making decisions. And you can build decoders that translate the computer's binary language into something we can understand, like letters on a screen. But to build a truly powerful machine, we need one more crucial ingredient. Right. But our computers do way more than just calculate. They remember things. They store our files. They remember what website we were on. This requires a completely new type of circuit, which is our next giant leap forward. This right here is the crucial difference. Combinational logic is stuck in the present. Sequential logic can remember the past. Its output depends not just on what's happening now, but also on what its state was before. The TV remote is a perfect example. To go to the next channel, it has to know what channel you're on right now. That simple act of remembering, well, it changes everything. The fundamental building block of memory is this brilliant little circuit called a flip-flop. It's basically a light switch. You flip it on, it stays on. You flip it off, it stays off. It holds its state. A single bit of information, a 1 or a 0, forever, until you tell it to change. This tiny, simple circuit is the atom of computer memory. There are billions of them in your phone right now, remembering everything from your Wi-Fi password to your high score and your favorite game. And by stringing these flip-flops together, we can create even more complex components. A register is just a row of flip-flops that can store a small amount of data, like a number the computer is about to do a calculation on. A counter is a circuit that can, well, count. It's essential for keeping track of program instructions and making sure everything happens in the right order. They are the computer's short-term memory and its internal metronome. All right, we have logic, we have memory, we have all the pieces. Now we're ready to scale up and assemble these components into the systems that form the very core of a digital brain. So this is where we scale up big time. We take millions or even billions of those flip-flops and arrange them into memory grids. This gives us things like RAM, or random access memory, which is your computer's temporary workspace. It's where your open apps and files live. We also create ROM, or read-only memory, which holds the permanent instructions that tell your computer how to wake up in the morning. And we can create programmable logic arrays, which are like these blank slate chips that engineers can customize for very specific tasks, from running a microwave to guiding a missile. So we've gone from a single switch to a full-blown memory system. But why does understanding this blueprint matter for anyone who wants to work in technology today? Let's connect the dots. This slide here really shows why all of this matters. It directly connects the concepts we've talked about to the skills that every computer scientist and engineer needs. See, understanding Boolean algebra isn't just some academic exercise, it's the absolute core of engineering knowledge. Analyzing circuits is problem-solving in its purest form, and designing memory systems, that is the very essence of creating new technology. This is the bedrock on which all of computer science is built. And this quote from the syllabus, it just gets right to the heart of it. It's not enough to understand the theory of an AND gate. A true expert needs to understand how that gate is physically realized in silicon. It's about connecting the world of abstract logic to the messy, beautiful reality of physics and electronics. That's where the real innovation happens. So let's just recap our journey for a second. We started with a simple switch, on or off. We gave it rules, a language of logic. We combined those rules to do math. Then we gave it a memory. And from those few simple building blocks, we've constructed the entire digital world. Every app, every website, every cat video you've ever watched can be traced right back to a simple, elegant cascade of ones and zeros. We've seen how engineers combine these basic blocks to create incredible things. And that leaves us with one final thought. Now that you understand the pieces, the logic, the memory, the procedure, if you could design the next fundamental component for a computer, what would it be? What new problem would you want it to solve?